Like alcohols and carboxylic acids, amines can behave as acids or bases. They have polar bonds to hydrogen, and so because of the dipole, there is a partially positive hydrogen, which can be an electrophile or an electron pair acceptor. Amines also have a lone pair on the nitrogen, which can act as a Lewis base nucleophile and donate electrons to form a bond to a partially positive hydrogen. So we're filling our dipoles. Whoa, wrong direction. So we have our nucleophile pair on the nitrogen circled in green, the partial positive indicated in blue. Also on top, the partial positive indicated in blue, and we can label them base and acid. And then the hydroxide is the base. It has both a negative charge and a lone pair. So the hydroxide, when the amine acts as an acid, the hydroxide base donates a pair of electrons to make a bond to the acidic hydrogen. Then the bond from hydrogen to the nitrogen breaks, and we form amide as a base, the conjugate base of methylamine, which is acting as an acid. And our acid that is formed is water. So hydroxide gains a proton to become water, our acid. I don't need to write water. Water is the acid in the product. And we can show which side of how the equilibrium favors, as the book indicates, the reactants by looking at the pKa's of the acid in the reactant and the acid in the product. And the pKa of the acid in the reactant is approximately 35 to 40. And the pKa of water is approximately 16. And as we said, the larger pKa acid is favored. So equilibrium favors formation of the acid with the higher pKa. Therefore, the book is correct. In the case of methylamine acting as an acid with hydroxide, the reactants are favored. When we look at methylamine acting as a base with protonated water, what we call hydronium ion, then in the products, the deprotonated water will be the base, and the protonated amine will be the acid. And we can see that the nitrogen in the reactant donates a pair of electrons to the acidic proton on the hydronium ion, and the H2O bond breaks, forming water as the product. We can identify which side of the reaction is favored by writing in the pKa's of the two acids, the acid in the reactant and the acid in the product. As stated previously, the pKa of hydronium ion, protonated water, is approximately -1. And the pKa of protonated methylamine for a protonated amine is approximately 11. 11 is larger than -1, and so the formation of the protonated amine acid is favored. So by equilibrium. So we'll say equilibrium favored. And you should be able to do this on an exam. Okay. So this is strange. Red mark in the middle of the page. All right. So here we have our approximate pKa's, summary of some of the pKa's that we've discussed to this point. Protonated alcohols, protonated carboxylics, and protonated water are all less than 0. Carboxylic acid has a pKa of approximately 4 to 5. The protonated amine has a pKa of 11. So if you look at the previous slide, it said 10.7 and 11, but here they're saying approximately 10. I remember 11 when I think of it. You guys can pick whether you want to remember it as 10 or 11, but these will give you a reference point for when you have to rank the molecules without having been given the pKa's. So there's going to be a lot of problems where you're asked what in all of these molecules rank them in terms of their acidity or rank them in terms of their basicity. And you're going to have to either know the pKa or know a periodic trend or know the functional groups in order to decide what's most acidic or what's the most basic. Okay. We can determine what the reactant or which is the stronger acid by looking at the pKa. And we know that if we have reactants, we can also determine which of the reactants acts as an acid by looking at the pKa's of the two molecules. Because the lower the pKa, the weaker the bond to hydrogen, and the more likely that that bond will break. The higher the pKa, the stronger the bond to hydrogen, and the less likely that that bond will break. So if we have reactants, we can determine only, and we need to draw products, we can determine which reactant is the acid by comparing the pKa's. For example, HCl has a pKa of -7, and H2O has a pKa of 15.7. If these two molecules react, HCl will act as the acid and water will act as the base. And the products that you should write would be that we form H3O plus Cl minus. When we have the reactants of ammonia and water, as shown on the right, we can determine which is the acid by evaluating the pKa's. Water having a pKa of approximately 16 and ammonia having a pKa of 36. Water is the lower pKa, and so it will behave as the acid, and ammonia will behave as the base. And the products of the reaction you should be able to write out would be water having one less proton, forming hydroxide ion, and the ammonia gaining a proton, trying to circle the negative charge. Okay. Negative circle. Okay. The ammonia will become protonated to make ammonium ion with 4 hydrogens and a positively charged nitrogen. The pKa of the protonated nitrogen is approximately 11. And we can say that because the protonated ammonium is the acid in the products, it has a lower pKa than the acid in the reactants, and this reaction will favor reactants. For the reaction with HCl forming H3O plus and Cl minus, we know that H3O plus has an approximate pKa of -1. -1 is greater than -7, and so in the case of HCl reacting with H2O, this reaction favors products. Okay.